I would like to thank the organizers for opportunity to come to this lovely place. I was walking yesterday, it really looks like Harry Potter land. And people speak language that I thought I knew. Anyway, thank you so much. So I'm going to talk about boson stars in AdS. So that's work that's already been published with two gentlemen, Steve Liebling and Luis Lerner. And I should say that without these two people, the work would not have come about because it heavily relies on numerical simulations, in particular a code that has been developed by Steve over the years. And so this is an ongoing project, and the reason why it is ongoing because the longer we stay in this subject, the more questions arise rather than answers, and so there will be more work to appear, and in particular with my student Venkat. So let me give you the standard spiel about AdS-CFT. So AdS-CFT is just a correspondence. On one side, we have some strongly coupled gauge theory or some strongly coupled interacting system. And on the other side, we have a string theory. And so the beauty of the correspondence is that it allows us to address questions in strongly interacting systems over which we do not have a control otherwise. The nice thing is that in principle, the simplest example of this AdS-CFT correspondence is when the central charge of the system at the UV fixed ultraviolet fixed point is infinity, and so the coupling is also infinitely strong. However, in a string theory, if we really use the AdS-CFT correspondence rather than phenomenological examples of it, there are systematic ways in principle how we can come closer to realistic systems. Having said that, I have to warn you that I'm not going to describe any realistic systems. And so everything that I'm going to talk about is a toy model, even though, and in particular, even though this toy model can be thought as, you know, n equal 4 super Yang-Mills, but it's not any real system that we have a lab access to. So for me, the interest in using AdS-CFT evolved towards understanding dynamics of the system. And so in particular, how strongly interacting system behaves if it is far from equilibrium. And so one of the things that, you know, natural to expect that if I have an interacting system and I perturb it far away, so it's far from equilibrium, and I allow it to evolve, so the constituents would scatter and interact. So eventually the system would equilibrate. So it will equilibrate, maybe it will thermalize. Okay, so I would actually thought that it would thermalize. The type of questions that I would like to address is this actually expectation true? So is it really happening that a far from equilibrium system during its unitary evolution will end up in equilibrium state? Will it be a thermal state? So does turbulence or turbulent instabilities play any role in equilibration? And then something that you might also wonder, suppose that there are some conserved global charges, and so you are evolving the system, so how would the equilibration occur in that case? So the point is that once you have a charge, then you expect probably equilibration in the superselecting in the superselection sector. So in the sector where the charge is conserved. So how all this plays around, so we try to make the first steps in understanding these questions using AdS-CFT correspondence. So this is the outline of my talk. Yep.
Is there a reason to expect that the conserved charge might prevent equilibration?
Well, you know, naively, that's what we saw. Sorry?
What?
Well, you know, so, okay, so suppose the equilibrium configuration, yeah, you could say that if the chemical potential is 0, right?
Well, there is an extreme case when you have an infinite number of concept charges. In that case, of course, because of integrability, typically.
Right. So,
Of course,
yeah,
whether
so-
you can do it with one is a different story.
Answer is no.
But with
Walter,
one,
sir.
with one surcharge, we can say it's changing the definition of what you mean by equilibrate. We talk about equilibration as ergodic motion and the fixed charge surface.
Yeah.
Just a question of what you mean by
It
it.
depends on
Is
what
that
you
what
use.
you mean by equilibrate? Yeah.
right. So I will be very precise in this context what equilibration means. Yes. Well, thank you. Thank you for this comment. Yeah. So the idea was that there will be a different trajectories in the phase space as the system evolves, and so maybe maybe if well, definitely if there are infinitely many conserved charges, then the system will stay in the same state.
Before you get to it later, what you're saying is that if there is a conserved charge, it might prevent equilibration even among the configurations that have that same amount of charge. Are you saying something like that? That's surprising.
Not true.
He's not saying that.
Not
Okay.
true.
Right. So there are a lot of things that intuitively we expect. So, for example, we would expect equilibration, and I will show that what's
So I
what's
guess
real.
in your context here, of the collapse that you're going to tell us about, of course, if you have a charge,
There will be a charge. Yes.
and the
So-
endpoint will not necessarily be fundamentally different than what you see.
Right. So if you wish, we can pose a a very sharp question. So we will have a configuration, and that initial configuration might or might not have a charge. And then we ask the question: how long does it take for a charge configuration equilibrate compared to configurations that do not have charge? All right. So what I'm going to do, I'm going to review this groundbreaking work by Bizon and Rostorovsky, which started the subject. And so I will explain what they presented as a mechanism for equilibration. So those people not only made, I would say, the first work towards addressing the question how strongly interacting system equilibrates, but they also came up with a mechanism for the equilibration. And so I will explain it, and I will say why I'm a little bit unhappy about this. And then I will go and discuss boson stars in AdS. So I will try to motivate why we are doing this. And the main motivation is that precisely we want to start with the different initial conditions and evolve different initial conditions to see how equilibration changes, if any. I will explain what the boson star is. So I will briefly discuss their properties. And then I will study linearized fluctuations about boson stars and argue that those are stable configurations. So then what we're going to do, we're going to do a numerical simulation of boson stars and their cousins. I will call them fake boson stars. I explain where the name comes from. And then what we found surprises we encountered surprises in these simulations. And those surprises forced us to go back to the original Bizon and Rostorovsky work. And so we rerun their simulations. And so I will explain what is going on here. And so that throws lots of questions. And so I will conclude with some further direction. Okay, so please interrupt me at any time, and I will try to answer the questions that you ask. So basically what Bizon and Rostorovsky did, they studied gravitational collapse of a real scalar field in global AdS4. And so the idea is that AdS4 corresponds to 2 + 1 dimensional strongly interacting system on the boundary. And so you prepare initial state, and this initial state is provided by the initial configuration of the scalar field. You can think of this that you have a quantum field theory, and at time t = 0, you prescribe expectation values of all the operators in this field theory, and you allow it to evolve. So the evolution on the field theory side of the story corresponds to gravitational collapse in AdS4. And the thing is that a fully quantum evolution on the field theory corresponds to a classical evolution in the bulk. And so everything that I'm going to talk about on the gravity side is just classical equations of motion and classical dynamics. So we have a four-dimensional effective action. So over here I have an Einstein-Hilbert term. I have a negative cosmological constant. And so Bizon and Rostorovsky, they looked at the real scalar field. And so instead what I'm going to do, I'm going to look at a complex scalar field. You know, it's just a trivial generalization, but having a complex scalar field allows me to put a charge as I do the evolution. And so this manifold M4 is a boundary where my field theory lives, plus a radial coordinate. So this radial coordinate plays the role of the renormalization group flow direction. And so I'm doing the simulation in global AdS. So what this means is that my field theory lives on a two-sphere in this case. So it lives on a compact manifold, and then there is a time direction. So the radial coordinate, which I call x, extends from 0 to pi over 2. So I'm gonna basically talk about 1+1 dimensional simulation. So I'm going to put a very strong restriction that during the evolution there is SO3 symmetry and it stays unbroken. So the reason why I'm imposing this condition just simply is that I have to deal with a 1+1 dimensional PDE instead of higher dimensional PDE, and we're already having problems here. So until we fully understand how to deal with gravitational PDEs in this case, maybe far in the future we will move to more general case. And so in this case, I can parameterize my line element as follows. So there is a metric function A, and then there is this metric function delta. Both of them are functions of radial coordinate and time. And then on top there is a scalar field, which is also a function of x and t. So it turns out, so this is something that we have heard yesterday, that there is a relation between the mass of the scalar field in the bulk to the dimension of the operator on the field theory side. So in this case, I'm talking about a massless bulk scalar field. So that corresponds to probing my non-equilibrium quantum field theory with a marginal operator. So that's a dimension 3 operator. And so as usual, when I look near the boundary expansion of this scalar field, there will be a non-normalizable component and there will be a normalizable component. So non-normalizable component corresponds to couplings. And in principle, you can do a simulation where you can think that you are changing the marginal coupling as a function of time, or you can set it to 0. And then what you are doing, you are really taking 2+1 dimensional conformal field theory and you are perturbing it by specifying initial condition of dimension 3 operator. So it turns out, so if you do that, then depending on the dimensionality of the operator, the scalar field dies as you approach to the boundary. And so in this particular case, what would happen is that, so the boundary, x at the boundary is at pi over 2. So if I introduce a boundary coordinate minus x, so my scalar field behaves some number times rho cubed. So that's, that coefficient is related to the VAF of the dual dimension 3 operator, right? So there will be a dimension 3 operator, and so this coefficient is related to its expectation value. However, what we found that it's very difficult to actually do the numerical simulation in sort of this normal field phi, and so instead, what we had to do, we had to rescale variables in such a way that our Hackett field phi, the one that I introduced here, actually vanishes. So it vanishes, but it vanishes linearly. So only in this situation we have been able to construct a stable code. Okay, so the problem is very simple. So you can give it to a student and derive an equation of motion. And so these are equations of motion presented here. So we introduced a momentum for scalar fields, and so this capital phi is basically related to the derivative of the scalar field. And then there is a first order equations for the metric factors A and delta. And in addition, there is one constraint equation. So I put a star here because I'm a little bit lying to you. So those of you who are mostly familiar with AdS CFT correspondence in static backgrounds, you know that there is also a constraint coming from GXX part of the metric. And so indeed, when I was writing equation in this way, I actually used this constraint and I got rid of 1 second order equation with respect to XX, which is nonetheless consistent with all the equations I wrote. So in other words, the set of equations that's on this page plus one additional equation here provides a full set of equations for the dynamical evolution. Good. So we're interested to numerically solve these equations, and we have to solve it subject to appropriate initial conditions. So at the boundary, we impose the conditions that we have only the normalizable modes turned on. So in particular, what this means is that this is a rescaled scalar field near the boundary. As I was saying, in order to guarantee stability of the simulation, we had to rescale it so that it vanishes linearly with near boundary coordinate. And then the metric factor A has a normalizable component. So this basically this constant m. You can see that it behaves 1 minus m rho cube. And this is the expected behavior because if you wish, metric deformations are marginal as long as you keep asymptotically AdS spacetime. And then there is additional metric factor delta, so you can see where it comes in. So, so it's basically part of the GTT metric factor. And so as we approach to the boundary, A goes to 1. And so in order to have evolution with a fixed field theory time, we have to impose condition that this delta goes to 0. Okay, so those are the boundary conditions near the AdS boundary. And that's it. So we do not put by hand anything additional. Now, when we do the simulations, we start simulation in without any horizon. So it's just AdS. And so at the origin of the space, we simply impose the regularity condition. And so those are given by these initial conditions here. Okay, so any questions about the setting of the problem? So, all right, so let me say one word. So you run the simulation, and so we would like to interpret the gravitational data in terms of field theory data. And so something that we can compute much more, but something that we can easily compute from the field theory perspective is the stress energy tensor, the boundary stress energy tensor of our field theory. So in this case, what happens is that it actually doesn't have any useful information because we have a unitary evolution, and so when we start with a given initial condition which has given mass or given energy, so this mass is going to be conserved. And so the conservation of the stress energy tensor is simply equivalent to this momentum constraint equation on the gravity side. So what we can also compute, and this is an interesting observable, is the expectation value of this dimension 3 operator. And as I was alluding to, it's simply related to the near the boundary asymptotic of the scalar field. So, so as you do the evolution, you simply extract this coefficient, and it tells you the expectation value of the operator. So the reason why you might be interested in this is because if there is any turbulent behavior or you expect the system to approach to equilibrium in some particular way, you might want to study this expectation value, right? So some things that we have done, we did a Fourier analysis over here, and we tried to understand are there any signatures of turbulence. So that's this is observables that you would do. Now I want to emphasize that that's a very limited class of observables. So I looked at a one-point correlation function. And of course, the field theory is much richer. So you can ask the questions about higher point correlation functions. You can ask the questions about the behavior of entanglement entropy, Wilson loops, so some non-local observable. And so this is something that could be done. It hasn't, my understanding is that not much of this has been done in this context, but given the working code, it's not a big deal to measure this observable. Additionally, the configuration, because I have a complex scalar field, the configurations that I simulate might carry a charge. And so this is an expression for a charge. So there is some formula over here. What I want you to pay attention to is that the scalar field has two components, right? So it's a complex scalar field. Phi is equal phi1 plus I phi 2. And so whenever I have phi 2 equals to 0, something that I'm simulating actually doesn't carry any charge. And so those are the original Bizon-Rostorowski simulation. And so whenever I want to compare charge simulations or to the neutral simulations, all I have to do is to set the scalar to 0.
Not completely clear to me what's happening with field theory, right? So you start at negative time and you have your field theory in equilibrium, and then you do some kind of...
No. I do not start the field theory at equilibrium. So I prepare an initial state on a field theory that I want to evolve.
Yeah.
Okay.
No, but you can always view it as some kind of quench, right?
You could do that. So for that, you would have to evolve from minus infinity. And I absolutely...
I just want to know what your initial state exactly is. In what sense is it out of equilibrium?
I'm not saying that initial state is equilibrium.
I want to know in what sense it is out of equilibrium. What kind of physics are you...
Oh, okay, because I can ask, right, so because I know what the very good question. Yes, very good question. So the initial conditions that I have, so first of all, if you ask me this question about field theory, to specify completely the state, I have to tell you all the correlation functions.
Yeah.
But, so I did not do that because I cannot. I'm not powerful enough. But what I can tell you is that there is one correlation function, which is the expectation value of the stress energy tensor, and that's a mass. Okay, then I can ask the question. So if I have, this 2 plus 1 dimensional CFT, and I have a non-zero energy, what is the equilibrium state? So the equilibrium state here is a thermal state with this particular energy. Okay. And so on a AdS side, that would correspond.
Density of matter.
That's right. So except that here I can talk because my CFT is in a finite volume, so you can divide by a volume. So that would be finite uniform energy density distribution, and so equilibrium state here would be a black hole. Okay, so it would be a thermal state which would be dual in the bulk to a black hole. And so, in fact, if the way how the solution is written here, it's actually, the reason why I wrote it in this way is precisely if you set this guy to 0, okay, so then there will be no scalar field. I can solve, once I set initially this thing to 0, then the scalar field will be solved with over all times. The field would be identical.
No, what that is asking is something simple. Right? It's asking what is your initial condition. Nothing is what is
No. He asked why my initial condition is not equilibrium. What I said is that with given that my configuration has an energy density, the only equilibrium configuration here is a thermal state. Okay? And I'm saying that it is not a thermal state because it's not a black hole. For it to be a black hole...
It's simpler than that. So there's all this work on infalling shell, where you basically say I inject energy at momentum to time t is 0, and then I see how that evolves in a long time equilibrium state. You're playing the game, right? There's a scalar field out there, meaning that somehow you did this finite density, I guess.
Right.
One thing I could imagine.
So there is a
fine question, and then you answer it.
Yep.
One thing I can imagine is that your initial condition of the kind, you start out with a zero density state and suddenly you inject the conserved charge, and then you see how it evolves and whether.
I could do that.
How are you doing it? What are you doing?
Right. So I could have done this, and so if you've been here last week, Rob Myers.
Last week I'm the organizer, so
Good. But Rob Myers gave a talk,
I know.
and so that was a talk precisely along the lines that you were asking.
I just want to know in what regard you were different. You were not telling me what the heck you were doing.
So here the evolution is such, that's what I said, so the evolution is such that the energy is conserved. So I start at a finite energy, I'm not changing the energy density. So that's, if you wish, an evolution in a microcanonical ensemble, okay? And I start with an initial state where, say, suppose I measure the number density of some particles, and in an equilibrium, that average number density should be constant or something, and I say that, it's not constant. Okay, so, well, I'm lying. It's not true. So in equilibrium, this expectation value should be set to 0. Okay, and I'm starting my initial configuration where the one-point correlation function of this dimension 3 operator is not 0. So that's not equilibrium state. The equilibrium state would be a black hole
without hair.
Without hair, okay? So now I don't have a black hole, but I have a hair. But the configuration that I start has a mass. So eventually, if you evolve it, it should equilibrate, okay? So eventually, okay, so I'm running, but please keep us, no, but the thing is that this is an important thing because, once you understand what is going on, then what else other than a black hole could come up, right? So then it becomes, so when I first time heard about Bizon and Rostorovsky work, that's a some sense trivial statement. Because you start with the configurations where you have a strongly interacting system, you injected energy, you allow the system to evolve while you keep the energy density fixed. And so at the end of the day, it will thermalize, okay? And the thermalization is a black hole formation. What else could have happened, okay? So that would have been the, and the reason why I started working, okay, so I guess I started working because I thought that we can, that intuition is not quite right, and what we have found that it's actually much worse than that. So there are, that's why I will come and I explain what are the puzzles.
What's your initial condition?
I guess the initial condition is just a lump of scalar field sitting in AdS, but it's not just AdS because you have to satisfy the constraint, so the geometry is deformed from AdS. But you
have to specify whether the lump resides.
Yeah, but you have to specify this lump in such a way that asymptotically the spacetime is AdS, which means that it has to decay in a suitable manner near the boundary.
Right, but again,
Continue. I think.
no, I can stop. I can move to the. No, but we're touching on very important questions because the reason why am I so elusive when you ask what state you describe, just telling you that there is this one-point correlation function is not enough because as Paul is saying is that I have to, at time t equals 0, I have to specify the whole profile of a scalar field. And what I'm in a bulk, from 0 all the way to the boundary. And as long as the asymptotic of the scalar field has this initial value, so this is at time t equals 0, this is just a number. So as long as this number is the same, then all my initial condition will have the dimension 3 operator expectation value to be the same. It is not to say that the initial condition I start with is the same initial condition, because the scalar can do something completely different in the bulk. That's why I'm saying that in order for me to fully specify initial condition, I have to tell you the expectation value of all the correlation functions. And all the correlation functions, when you will be computing, then they will start probing how at time t equals 0 I specify my scalar field inside the space. And so when I will be talking about initial conditions that Bizon and Rostorovsky used and what we used, this is simply, those are the initial conditions which have the same or can have the same value over here, but they differ in a higher point correlation function. Okay? Yep.
I think you can say the same thing by stating that the initial state has a non-trivial expectation value, which you know at all energy scales, because one-point functions change with energy scale in general. And this is what your profile at the initial t value is.
Well, I don't know if I would say this. I would say what I said. There are other point correlation, higher point correlation functions, and you measure higher point correlation functions, so you will start probing your fully initial profile of a scalar field. So I think that's at least that's the statement I'm happy with. Okay, so let me make a quick comment on global or local charges. So over here, what you see I am doing, I'm talking about a complex scalar field, and I don't have, and I'm saying that I'm going to evolve configurations which carry a global charge. And people who do AdS CFT, then you could jump at me and say, and I don't know if people in the audience here did this when I was giving this talk earlier, but definitely some did. So I decided to add this transparency. Is that is not the way how we introduce global charge in AdS, right? So in order to introduce global charge, what you have to do, you have to introduce a gauge charge in the bulk. And so here I am not doing it. I say yes, I do that. So you can take this complex scalar field, you can add a gauge field, and you can do everything that I'm doing by simply saying that the chemical potential during your evolution you set to 0. So once you set a chemical potential, then the vector field will be identically 0. And so indeed, I would say that even though I also have a global charge in the bulk, in this particular situation, it is really corresponding to global charge on the boundary as well.
Sorry.
Yeah.
Can you make sure from the equation, so if you're gauging the U1 charge in the bulk,
Yeah.
Can you make sure from the evolution equation of the gauge field that it would stay 0?
Yes,
Okay.
because it's, yes.
No.
I would think it's coupled to the scalar field, so it's
You don't think,
It's true in the limit of weak coupling. You have a coupling constant you're adding, and you're studying the weak coupling limit. But that's which is fine. But it is the weak coupling limit, and that weak coupling limit you don't excite the gauge field.
okay. Okay.
definitely it's true in the weak coupling, but you're saying that any time at a finite coupling, that's not going to happen.
You've got a current, so it's going to source the gauge field.
Exactly right.
Yes, I agree. Yes. Okay, so now let me go to this Bizon and Rostorovsky and explain to you what the initial condition they started with. So this capital phi. So remember that capital phi is basically derivative of little phi, and so they prescribed initial condition when this guy is 0, and so pi is momentum of the scalar field, and so for the momentum of the scalar field. They prescribed this configuration. So notice that it's basically a peak. So you have a momentum which is peaked at the origin of the AdS space, so as x equals to 0. Now as x approaches to pi over 2, you have an exponential decay of this momentum. So this is an initial condition at time t equals 0. So over here, if you take this profile, and if you compute the expectation value, so in their case, the expectation value at time t equals 0 is equal to 0. So they start with their operator expectation value as it would be in equilibrium. Okay. On the other hand, as you can see, that this is not an equilibrium. There is some configuration. So notice that the profile is specified by two numbers, and so those two numbers is epsilon and sigma. Sigma is a magical number. It's 1/16, and so this is something that originally Bizon and Rostorovsky decided to keep magical. But what they did, they were changing epsilon, and so they started with a large value of epsilon, and they started decreasing it. And so here I want to give you an intuition, or at least why this was a surprise for the gravity community. Well, so people did similar stuff in Minkowski flat spacetime, and basically what you do, you have a collapsing matter, okay, that moves from the boundary into the origin, So there are two possibilities. So if your pulse of the, say, scalar fields that you are collapsing is sufficiently dense, then it will get inside its own Schwarzschild radius, and you will have a black hole formation. So, the other possibility is that if you start with a pulse that is sufficiently dispersed, then what will happen is that it will go through itself, right? And so it will just go back to the infinity. So there will be no collapse. And then whether or not you have collapse, you have this interesting Choptic critical phenomena. And so this was sort of the expectation from the gravity community, that something like this might happen in AdS, especially given the fact that the origin of the AdS behaves like a flat space. So instead, that is not what they found. So what they found is, again, quite an interesting phenomena, though a posteriori you could have guessed that this must have happened. So over here there are dots, and so x on the vertical axis, I'm telling you x, h. X is value of the horizon coordinate at which the collapsing matter gets inside its own Schwarzschild radius. So you can think of this as a black hole formation. And so epsilon is the amplitude of your scalar perturbations that you put on top of AdS space. And you can see that as you decrease epsilon, so you're forming smaller and smaller black hole, and at some stage over here, when epsilon is between 40 and 45, it looks like the black hole stopped forming. That if I wouldn't have shown you the rest, okay? And this is really the situation that happens in Minkowski spacetime. So the pulse collapses, and when epsilon is too small at this point, then it simply goes back. Okay, the horizon is not formed, and the pulse managed to get all the way to the origin of the AdS space. Now in AdS, in Minkowski spacetime, what would happen is that after the pulse goes through the origin, it would go to infinity, and you would never see it back. So AdS behaves, is a gravity in a box, and it is gravity in a box with a perfectly reflecting boundary condition. Moreover, so the pulse, so I have a massless scalar field, and a massless scalar field travels along null geodesic, and it takes finite time. So you can compute, and it takes pi in my units, where radius of AdS is equal to 1, it takes pi to reach the boundary. So what would happen in this case is the pulse, if I wait pi seconds, the pulse will get back to the boundary, where it will get reflected and then has a chance to go back into the origin of the AdS space. However, during this motion, gravity acts on the pulse, and gravity has a focusing effect. So even though initially pulse was not dense enough, the pulse has been traveled back and forth to the boundary, so it got compressed from the gravity, and so on the second pass here, it actually collapsed. And so over here, you see successive collapses as you decrease the value of epsilon, and I'm calling it successive because in order to get to these curves, what you need to do, you need to have more bounces of a scalar field in this boxed gravity. So they did this simulation, and then they concluded that any initial configuration would lead to a black hole formation. Okay, so everything, everybody was happy, and everything looked trivial when I said it must have been trivial when what they found. Well, but they did much more.
There is this notion that the time it takes is kind of anomalous. You have to.
Right. So you have to be very careful. Right. So you have to be careful. So that's why I don't want to go into this detail, especially because I'm doing simulation in the Spefferman-Graham coordinates. So from the perspective of the outside observer, it takes an infinite time for a horizon to see the horizon. However, it takes finite time for me to make a statement that there will be no more bounces. Okay, and so that's when I'm going to talk. This will become even more important for my plots, because in their case, they talk about horizon formation. They also mention the time as well. But when I talk about the time, So this is basically, then I have to become flapping my hands, because at some stage I have to say that that's how long I have to wait, and I'm sure that there will be no more bounces after that time. So that's a good point. Good. So, but they did much more than that. Not only did they come up with this idea that any initial configuration in AdS, if you allow it to evolve, will end up in a black hole. They actually provided a mechanism for this collapse. So let me explain you this mechanism. So again, the problem is complicated. We cannot solve it analytically, but we can get an analytic handle if we do a small amplitude expansion. So what you can do, you can say, I'm going to expand my field phi, and it will have an odd powers of epsilon. So remember that epsilon was the amplitude. And so the metric factors will have an expansion in even powers in epsilon. So you plug this thing into your PDEs, and you collect. So you can plug this in, and in order to proceed, you have to choose a nice Fourier space in x coordinate. And so this nice Fourier, I shouldn't say space. A nice Fourier modes in which you decompose these functions, and so that is provided by what we call oscillons. So oscillons are just normal modes of a massless scalar field in AdS. So those are linearized modes on top of AdS. So they have a frequency. So in our case, so there are infinitely many of them, and so their frequencies is characterized 3 plus 2j, where j is 0, 1, up to infinity. And so there is an explicit expression for the profile of this oscillon. Moreover, those oscillons, you can they are orthogonal, and so you can normalize them to be 1. Okay. So then the idea is that you start with the initial condition, you expand your initial condition in this oscillon basis, and then basically you do Fourier time Fourier transform in these frequencies, and then you convert your PDEs into the ordinary differential equation along the x coordinate. So they did this analysis to order epsilon cube, and they found they made a remarkable observation. So what they found is that if you prescribe, so you have to prescribe initial condition, and so initial condition, my scalar field at time t equals 0, 0, I can decompose in this oscillon basis, right? And so I'm going to assume that this Fourier coefficient Ci are for the 1. Ci are for the 1. And so what they found is that at the first nonlinear order, there is a resonance phenomena. The reason why there is a resonance phenomena because the frequencies of this omega j that you cook up your initial condition have commensurate, and so in particular, if you start with if your initial condition contains oscillons at levels J1, J2, and J3, so you can show that there are resonance frequencies which satisfy this condition. So you form all possible triplets as long as this number is positive. And then depending whether or not you turn on this resonance frequency in the initial condition, you get an instability. Okay, so let me be more specific what is going on here. So let's consider a single oscillon, and what I mean single oscillon, that all this infinite sum at time t equals 0, I'm just going to say that there is a single mode that is being excited with amplitude epsilon, and that's the lowest linearized fluctuation. So I can plug in the equation and I can solve it, and so here I'm presenting a solution to order epsilon cube. Well, so you can see that at order epsilon cube, there is a mode which oscillates with the same frequency as I started with, and then there is a mode which oscillates with the frequency 90. So it's actually easy to understand how these guys happen, because your scalar field acts quadratically on the background. So basically you have to square whatever omega t you have in your scalar field, and then the back reaction on itself appears at the cubic order. So you end up basically having omega cosine omega it times cosine times cosine. So that's going to be a back reaction at the third order. And so then when you decompose triplet products of cosines, you basically have to add or subtract frequencies. So that's in particular how a number 9 comes, right? So in this case, you sum 3 frequencies. Now, if you look at this solution, that is not the way how you find the solution, okay? Because notice here, I put epsilon squared inside the cosine. So rather, what you find is a Taylor series expansion of this cosine. And if you do Taylor series expansion of this cosine, you will find out that there is this term which grows with time. So this term is epsilon cubed t sine omega naught t. So what I did when I wrote solution in this way, I actually absorbed this time-growing solution into a shift, into a frequency shift over here. So the reason why I want to do that is if I am unable to absorb this time-growing term, then it appears that the amplitude of my scalar field grows with time if I include nonlinear effects. However, if such terms is possible to absorb into a frequency shift, then all I am saying is that if you include nonlinear effects, your linearized frequencies, which are 3 plus 2j, get slightly shifted. And so the point is that if you start with a single oscillon, you can do this shift. Now, suppose you look at the initial condition where you have 2 oscillons initially. And so then, again, you just solve the equations of motion at order epsilon cube, and you will find out that here there are 3 terms that grows with time. So that's epsilon cube t, omega naught, omega 1, and omega 2. And so those are the terms corresponding to the frequencies 3, 5, and 7. Now, because at order epsilon, I already had oscillons of frequencies 3 and 5 excited, I can absorb 2 of the time-growing terms into the frequency shifts of 3 and 5, but I cannot do it with a frequency 7. So the way how frequency 7 occurs, so remember that I was telling you that the resonance condition is omega I1 plus omega I2 minus omega I3. So the way how, and so all these, they are resonance frequencies. And so the resonance frequency 7 occurs as 5 plus 5 minus 3. And this frequency has not been present at order epsilon, and that's why I am unable to absorb this. And so this term appears as genuinely instability. So I have a linearized perturbation, and once I include a leading nonlinear effect, I see that the amplitude of this perturbation grows with time. And so what Bizon and Rostorovsky said is, this is the origin why for any epsilon, because remember that the claims they were making is doesn't matter what initial condition you have. In particular, it doesn't matter how small the amplitude you have. If you wait long enough, it will eventually collapse. And so what they were saying is that because when you specify initial condition, they were thinking in terms of you have a finite number of these oscillons present, then you will always find some mode that will be growing with time. And so as this mode will grow, it will start populate all other modes. And so eventually that would lead into a black hole formation on AdS space. So that's very nice. However, so as I said, that's basically the crust of Bizon-Rostorovsky argument for weakly nonlinear instability, and they claim that it's universal generic. Now, I think it's wrong, or at least misleading. And so the reason why this is the case, so these arguments work only if you think that you have a finite number of oscillons. However, if you have an infinite number of them to begin with, so the reason why I had a problem with the frequency 7, because I don't have it excited at order epsilon. So let me excite at order epsilon frequency 7, then the frequency 9 has to be excited. So basically, all these arguments tell you that you have to have oscillons of all frequency excited at order epsilon to be able to provide this epsilon squared shift. And so indeed, you can look at the analysis and you will find out that if at order epsilon, you have a linear superposition with some amplitudes a sub j, then you can absorb all nonlinear effects, all these time-growing amplitudes into the frequency shifts, provided that this sum is convergent. Okay, so then here, the condition whether or not initial condition at small epsilon would lead to instabilities get phrased into a question under which condition I need to have all the oscillons excited, and so under which condition this sum will be convergent. Notice that in this sum there is this resonance frequency which I was explaining how it arises. And so there is this amplitude corresponding to this resonance frequency presented at order epsilon. So in our case, what was going on is that the oscillon of frequency 7 was not excited. So that amplitude was 0. And that is why we ended up with instabilities. However, as I said, this argument it doesn't look convincing once you realize that all it simply tells you is that you have to have an infinite set of oscillons present.
So Alex, under what sort of conditions does that sum tend to converge?
That's a good question. I don't know the answer. However, I will present you specific examples. Okay, so in this problem, we are sort of in an experimental view. So some things that we're going to do, and I will not have time for that to explain that, but some things that what we're doing now is providing a different spectral decomposition of initial data in terms of oscillons, and starting depending on the asymptotics of the spectral profile of this. Basically, how does this coefficient has to behave, Ci, as a function of I when I is large, right? So there should be some power here, some negative power.
Isn't the power just dictated by how smooth the function is, whether it's C2, C3, something like that?
We don't know that yet. So I will give you some of the details. So for example, it definitely is, so if this Ci, again, just from experiment, is say 1 plus I to the power minus 6, then it must be convergent, because I give you a specific example where I have this infinite set of oscillons with this particular power law decay, and I have a convergence. So this sum, I give you an example when if that power is not 6, but that power is between 1 and 2, and it is not convergent anymore. Okay, so this is something that, that still is necessary to understand. Which initial conditions result in collapse, which one do not. But because I want actually to tell you what the puzzle is. Yes, I know, 5 minutes. So, so what we try to do, we actually try to see to which extent we believe this Bison-Rostorovsky argument. And so in particular, is it possible that any configuration would collapse? And so that is a reason why we started looking at the charge configuration, because the gentleman that is on the paper, Steve Liebling, he actually wrote a paper, a big review paper on boson stars. So boson stars are soliton-like configurations in AdS, and so under sufficiently, people expect them to be stable. And so what we were thinking is that those guys, Bison and Rostorovsky, they were saying that any initial configuration would collapse, but what if we start our simulation from the initial condition which is close to this soliton? How would, solitons are supposed to be stable, okay? And over here we have a charge, and so charge is something that that's supposed to protect against collapse. So that's all my previous arguments, charge versus non-charge symbolization. And that's what we did. And so these solitons are boson stars, so I don't have time to go through that. You can do lots of things here. And so here, going to Don's question, So if you do this you have an initial condition which is a boson star, and that's where this power 6 comes from. So you can do simulation of boson stars, which we did, and you show that it's stable. Now you can take your initial condition corresponding to boson star, small amplitude, and you decompose it in oscillons, and you will find out that that's a spectral decomposition. So boson stars provide an explicit example where you have an infinite set of oscillons excited, and you know at least how fast these amplitudes has to decay for higher levels in order to have the sum convergent. What you can do a simple linear stability analysis on top of boson stars, and you will find out that it's stable. This is just to impress you that we can do analytical result, and so these numbers are numerical, and we can actually compute, and all the curves fit nicely. And then we did the simulation, okay? So in the last 2 minutes, I'm going to really tell you what we actually did. So first, we started with the boson stars. We perturbed them, but then, what we did, because we have a boson stars which are charge configuration, and they are different from initial conditions that Bison and company were having, because their initial configuration was a localized pulse at the origin of AdS. These boson stars, they are distributed configuration. And so what we did, so there is a charge here, but then we said, well, why don't we compare to our new initial conditions to what we call fake boson stars. So those are distributed energy initial condition in the bulk, but they do not carry the charge. The reason why they do not carry the charge, because the second scalar field I set to 0, but the first scalar field I set exactly what it would have been for a boson star. In order for it to be a genuine boson star, both scalar fields has to be excited. And then we found a surprise, and because we found a surprise, we had to go back to the original Bison simulation. And remember, there was a magical number 1/16, and so that's when we removed the magical part of that number. Good, so let me show you the numbers. We had to use a fairly sophisticated code with adaptive mesh refinement. So I'm not going to go to show you what is going on, but what we found, okay, so this is a simulation of the real boson stars with a perturbation, and so this is so first of all, if you do not perturb boson stars, they never collapse. So that establishes the nonlinear stabilities of boson stars. So that's what we expected, but then we started doing a perturbation on top of that, and the perturbation is characterized by epsilon. As you can see that for sufficiently small epsilon, they do not collapse either. Okay.
Collapse time.
Sorry?
Your y-axis, you didn't explain what
it's a time that it would require to collapse.
Yeah,
So, so that's subject to the questions we had, subject to discussion we had before. So this is kind of what we expected. So that's not something unexpected that we found. So we started by looking at the charge configurations, which are solitons, so they are protected by charge. And so the idea is that we expect them not to collapse, but we also expect not to collapse configuration sufficiently close to that. So that's basically what it suggests. However, there is a surprise here, because there is a difference between charged and uncharged configurations. And you can see there is no dramatic difference. So I started motivating this, and that's a true reason. So we started thinking that, oh, we will make these solitons, and the solitons will not collapse. Well, we were wrong, because apparently being a soliton or not being a soliton is not a big deal. So whether or not you have an initial configuration carrying a charge is not the issue. So the boson stars have excited states, and so over here that's a ground state, that's excited state, the same feature. So what is going on? So that's where we encountered the puzzle, because it looks like that being a protected configuration like solitons, so if we would have discovered that solitons, solitoning configurations in the CFT configuration space do not equilibrate, that would not be a big deal. We would still write a paper and say that Bison and Rostorovsky, make two strong statements. There are these protected configurations, but that's not what we found. So it appears that what we found that it's not the question of whether or not you are protected by having a charge, but it's a question whether or not you have a distributed initial data. And the hand-waving argument here is that, yes, indeed, as the pulse bounces off, gravity tries to compress it, but there is also a nonlinear dispersion going on in the pulse. And so the question whether or not the pulse forms a black hole is a question whether or not the dispersion wins versus focusing effect of gravity. So once we realized this, we said, well, if we are right, then we should go back to the original Bison simulation and start changing sigma. Remember, the sigma was a magical number, which is 1/16, and that number was telling you how sharp your pulse is. And so indeed, what we found is that that's their simulation, which never collapse as you decrease epsilon. And so those for epsilon 1/16 and close to it, which simply tells you that in this case, the dispersion, you start your initial condition with sufficiently compressed pulse so that the dispersion of the pulse is not sufficient and gravity focusing effect wins. However, as you increase epsilon, as you increase sigma, what happens is your pulse becomes broader. And it resembles closer and closer this boson star initial conditions. And you can see that for some critical value of epsilon, small one, it stops collapsing. So that's what I would call a genuine finding, something that we never expected to happen. And unfortunately, we have, so this is just what I said in words. It looks like that with Bison initial conditions, there is this critical value of sigma. Yep.
I thought the case was that if you increase it even further, that it starts collapsing again.
Right. So you want me to skip conclusions, which I will. So then there was a paper by these fine gentlemen, Andrei Rostorovsky and his student. And so first of all, what we found is you could have asked why did Bison and Rostorovsky never changed sigma? They just didn't. But then they went back and they rerun their simulation on their code, which is a different code, and they reproduced our result. So they absolutely agree with that. And then somehow they they attributed to us the statement, which we never said, that it looks like we were saying that once sigma is larger than 0.3, everything will be collapsing in the initial condition. That's not what we said, but that's the way how they interpreted it, despite the fact that 3 of us met in Warsaw earlier this year, and before those guys posted the paper, they gave it to us, and we said, no, that is not what we said. They still post the paper. But that's related to the question that Veronica is raising. It turns out that if you start increasing sigma large enough, the things start collapsing again. And so why that is happening? Well, the reason why this is happening is because remember that you are creating a pulse, but the pulse you are creating, it's just e to the minus 1 over as you close to the boundary. So if sigma is very small, what I'm trying to say is that if sigma is very small, your pulse is very sharp at the origin of AdS. But if sigma is very large, what is happening is that your pulse is flat inside the AdS, but you have a very sharp profile of the pulse near the boundary. So
Not in terms of proper distance.
sorry?
Not as measured by proper distance.
Well, as measured by the distribution of oscillons. Okay, so here, this is what I was saying, that if I look at the spectral profile in this case, so the power is actually minus 1.2. So the way how I would interpret it, if you make these sharp features in your pulse, then the focusing effect will focus on your boundaries of the pulse, if you wish, and that would be enough to cause the collapse. Again, this is just a conjecture. So. Well, so see, what is going on is you increase the sigma, all your spectral decomposition approaches this, this red line, okay? And I am saying that this red line, if I were to decompose it in terms of oscillons, so it looks like that I'm still populating oscillons of very high number. Let me conclude. So basically. Okay, so the thing is that there is a lot of questions left in this subject. So we established that there are certain configurations in strongly interacting conformal field theory that does not equilibrate. We do not understand why they do not equilibrate. What is the mechanism that separate configurations that equilibrate compared to configurations that do not equilibrate? Let me mention some things that we are currently doing. So currently we are running the simulations where we extended our analysis to massive scalar field. So once you have massive scalar fields, that allows you to explore equilibrium versus non-equilibrium of operators of different dimension. And then we tested our distributed collapse idea in different dimensions. Over here, we already have result. And basically, you have the same feature in any dimension. And thank you. Sorry for...
Is there one urgent question?
So you cannot really formulate the criterion for this stability collapse on
No, we cannot. Unfortunately, yeah, so that basically our work makes problem more dirty and less clear what's going on. That's why we want to simulate all possible spectrum, ideally. The thing is that it's very expensive to do the simulation. Some of the simulation well, pretty much all the simulations we were running on supercomputers, and it was over a month to run a single simulation.
Have you tried the singularity functions for that? Analysis of singularities or mappings?
It's hard because the instabilities arise after a month of running, right? So I don't know. It's not like you know when you are close to these black hole formations. That would be great if there is some analytical intuition.
Okay, let's thank Alex again.